We're next going to talk about the three classic garbage collection algorithms: reference counting, mark sweep, and copying. In this lecture, I'm going to focus on reference counting and mark and sweep. These three algorithms together, all or in part, make up most of the garbage collection technologies that are in use today that you are familiar with in the languages like Python, Ruby, Java, and JavaScript. The two that we're going to focus on are reference counting and mark and sweep. These two use an allocation technique called free list allocation, where we keep one or more lists of free chunks from the heap address space in the process's address space of the executing program. We're going to break off pieces of these chunks to allocate to objects as the program requests them. The free list, again, is an internal runtime data structure. It's a linked list of free blocks that we can have represent all of the heap address space that's available in virtual memory of a process. Typically, there are multiple free lists, a small number of free lists, and each of them hold space chunks of different sizes. But that's beyond the scope of our lecture here, and in general, we're just going to focus on and assume a single linked list of free blocks that represent the free space in virtual memory of the heap of the process. We can imagine this memory as one big contiguous array with a set of addresses from start to finish, as depicted here at the bottom of the slide. On the right, I have in orange a representation of an object. Again, an object could be called a cell or a node. In all cases, the objects in our heap have headers. This header is going to hold information about the type of the object, as well as some other meta information used by the runtime system. The object then also holds a set of fields, as we described in earlier lectures. In this case, I'm just going to assume that there are two fields, just for simplicity. This address space is typically word aligned, and objects are what is allocated out in this space. The free list is a linked list data structure that holds the chunks that are available in the address space of the heap. There's usually a list head, a header of the linked list that holds the first address, and each chunk has a next pointer, which refers to the next chunk. If two chunks are contiguous, they will typically be conjoined and maybe put on a different list of a different size. But all in all, you can get to all of the free space in the process's heap area from this linked list or a set of linked lists. If you notice, what will happen here is we'll want to allocate objects throughout the heap, and objects will come and go over the lifetime of the program. As you allocate things, we start from the beginning of the heap or the beginning of the free list, and we start allocating from there. But over time, objects are deallocated, and that space is returned to the free list. And so what you have is a heap area that has free chunks interspersed with objects. And this is called fragmentation. The heap is fragmented. That is, they are the set of the free area is not contiguous. And this fragmentation can increase over time. And in fact, it may be that there's no space in your heap that can fit a particular object. So say we're going to allocate an object and it's large, but there's no contiguous free space to hold it, then you will run out of memory. Even if you had put all the fragmented spots together next to each other, it would have been enough to hold the object. If that space is not contiguous, that object cannot be allocated there. As an example, I have a large object, and in the program, the operation is to allocate an object of this type called large object and return its address after the object is being constructed, that is initialized, return its address to the program and store it in H, the variable H. Also in this picture, I have a bunch of other variables, A, B, C, D, E, F, G, H, I, J, K, L. And these are just variables from our program. They could be from any of our roots, from the statics table, that is the globals, or from local variables in stack frames on the runtime stack, or in our registers that the CPU is operating on. Each of these variables can refer to an address out in the heap, and I have some arrows here in black that show these variables referring to the heap objects out there. Some of the heap objects have values, scalar values in their fields, and all objects out in the heap in this example have 2 fields and a header. Some objects have null in one of their field values, and other fields hold scalar values like 6 or 2 or 7. So I want to allocate this object at this program point, and so I look for the first available contiguous area that can hold this object, that's big enough to hold this object, and then I update the next pointer of the free chunk that occurs prior to this object and have it point to the free chunk that occurs after this newly allocated object. I also return the address of this object where I allocated it to the program and store it in H. This is depicted with the green arrows in this example. Our next instruction assigns null to D, and in this case, right before this instruction executes, D is referring to an object in the center of the heap that has 2 fields. One holds the value 2, and one has a reference to another object. When I make this assignment after this instruction executes, D holds the value null, so it no longer holds an address out to the heap, so it won't be chased, and the space that D was referring to, that object, can be reclaimed, and the space can be added to the free list. The first basic garbage collection algorithm is reference counting, and the idea here is that we're going to add an atomic field to the header of every single object, and that field is going to hold the reference count for that object. That is the count at a particular program point of all pointers to that object from roots or from other objects in the program. All cells in the free list, or all objects on the free list, have a count of 0. There is a head of the free list stored in some variable or some register that the runtime can get to, so that we can easily allocate new objects from the heap. Every time there is a pointer update that changes the value of the pointer to refer to an object, the reference counter for that object in its header is incremented. Every time a reference is removed, the count is decremented. If ever the count goes to 0, there is no way for the program to access that memory. That is, that memory has leaked. It is no longer reachable. Therefore, it is garbage and can be cleaned up. So with reference counting, this algorithm is going to return such objects, and that is, objects that have their count go to 0, to the free list as soon as those counts go to 0. In this slide, we show the abstraction for the different algorithms associated with the reference counting garbage collection algorithm. When we want to allocate a new object, we call the function new in the bottom left. In this case, we're going to check the free list to see if it's null. If it is, then we're out of memory. We have no more space to allocate. Assuming we have space on the free list, we call the allocate routine. The allocate routine chops off a chunk of the free list big enough to hold the type that we're asking for. And it's going to update the head of the free list to point to the next pointer, that is the space that follows the object we just allocated. We then return the address of the object we just allocated. Back in new, we take this address and we assign it to new cell. New cell then has its reference count set to 1, and we return this address to the program. Another example on the right is an update. This is where we want to assign the leftmost field of an object to S. So we have a variable R that refers to an object, and we're going to change its leftmost field to point to an object referred to by S. In this case, the update function is called. The first thing we do is we increment the reference count of the object pointed to by S, the object that is referred to by the variable on the right-hand side of this assignment. We then call delete on the object that our .left is pointing to. In this case, that got passed into this function, so R's left field was passed in, and now we're referring to it as R. So we're calling delete on R, which is calling delete on the left field of the R object in our example. Delete, in the delete routine, we decrement the reference count of the object referred to by this address. We then check if the reference count has gone to 0. If it has, we chase all of the children of this object and decrement and call delete on their reference counts of the objects they point to. Once we have completed all that, we return. And again, so this is our recursive algorithm. When we recurse back out, once we've addressed all the children and we have chased all their children, so we're doing a depth first chase, traversal. And once we recurse all the way back out, we then call free on the object that we started with, in this case T. When we're done, we return to the caller, which in this case was update. And in this case, we're updating, we invoke the last instruction, which is assigning what R points to S. So that's going to cause the left field of the R object to be assigned to S. One thing I didn't go through is the free routine. When I call free on an object, I just return it to the free list. So I'm going to add it to the front of the free list and update the head of the list. In the bottom right, I have the example of this update of what the state of the heap looks like before and after. The values in the headers are the reference counts. So in our next example, what we want to do is we have an object referred to by the variable R, and we want to change its right field. We want to update it to the value null. And the current state of the heap is shown below this instruction. So we have an R object, a T object, and an S object, and a U object, and a V object. The left field of R refers to T. The right field of R refers to S. The fields of T are scalars and not shown, their values are not shown here. The fields of S are references. The left field points to T, the right field points to U. In the U object, we have two fields. One's a scalar, the left one. The right one is a reference, it points to V. And the V object has two fields and it points to scalars. There are no pointers, so the values are scalars and not shown here. In every object, we have the reference count. And so when we invoke this update, that is, we set the right field of R to null, the first thing we do is we call update on R arrow right and pass in the value null. In our update routine, we're going to update, we're going to increment the reference count on the value the address that was passed in, but since the value is null, we're not going to do that because it's not an object. So the next thing we're going to do is call delete on the right hand side of this assignment. So that is R arrow right. R arrow right, that is the right field of R, is going to be passed into the delete out routine. The first thing we do in the delete routine is to decrement the reference count. And as you can see on the right side in the drawing, we have decremented the reference count of S. At this point, we're going to chase its children, chase the children of S, because that's the next thing we do in the delete routine, because the reference count has gone to 0. Next thing we do is when we're chasing the children, we call delete on each of the children. So we call delete on the U object. That's going to decrement the reference count, and that reference count is going to go to 0. So we're going to recursively call delete on its children that are fields that have references in them. And that's going to be the right field of U, which points to V. So we're going to call delete on V. It's going to decrement the reference count, and it's going to go to 0. We're going to chase its children. There are no children for V that are references, and so we're going to call free on V, and that's going to cause V to be added to the free list. We're going to recurse backwards, and that will cause U to be added to the free list because we've chased all of its children and called V and called free on it. We're going to recurse back up to S, and we're going to put S on the free list because we have chased all of its children, and its reference count is 0. Call free on that. That goes to the front of the free list like the other ones have, and we have the figure as depicted on the right. There are many strengths in reference counting garbage collection, and the main one is that it's incremental. That is, we never fully clean up the heap at any one garbage collection event. Incremental collection means we're only collecting a portion of the heap at a time. This allows for a smoother response time because we're interleaving the execution of the mutator with the cleaning up of a small amount of garbage. The other nice thing about reference counting is we have locality of reference. If you think about your program is accessing a certain set of variables and changing pointers around in those variables. So you're potentially accessing those objects to which those variables are referring. And so those objects are going to have their addresses and their data in cache. By also just touching through garbage collection the objects that the program has recently accessed, we're probably going to also refer to objects that are in cache, and we're not going to bring in new objects, or we're not going to bring in too many objects into cache, hurting the memory hierarchy performance of the program. So we have this locality of reference that is very similar to the program itself. The other thing is, along these same lines, is that we can reuse cells that have just been recently reclaimed. That is, if we just allocated an object if we just freed an object, we can allocate a new object using that space. And since that is a recently used, potentially, object by the program, some of its addresses might be in cache, and we might get a benefit from that. Also, if we are allocating the same type that was just freed, we have the basic structure that we can leverage so that we can really quickly initialize the object without constructing a whole new object. That is, update in places possible. But there are also many weaknesses of reference counting. The first one is that every time a variable with a pointer in it, that is, a variable that holds a reference, an address, that is a dynamic variable, is updated. Every time a variable is updated, we have to stop and we have to check the reference counts and update them and potentially delete some garbage. And so because we're interrupting the program a lot, there's a lot of overhead introduced for every single pointer update. The next thing about reference counting that is a weakness is that it's very fragile. When we're writing or developing a garbage collector that is a reference counting garbage collector, it's hard to get the increments and decrements right, and it's hard to maintain this garbage collector. The next thing that's a weakness of reference counting garbage collection is that there's extra space added to each cell or each object in its header to hold the count. We have to hold enough space, or we have to have an alternative for what happens when that space overflows. The biggest weakness of reference counting garbage collection, however, is cyclic data structures cannot be reclaimed. If you look at this example at the bottom, what we have is we want to remove the reference from the right field of R to S. When we do so, because S is the start of a doubly linked list, we decrement the reference count of S, but it never goes to 0. So therefore, we never chase its children, and therefore we can never clean up this cycle. So cyclic data structures cannot be handled. We're going to have to use something else, like another garbage collector, to clean up these pieces of memory, or we're going to have to make the garbage collector very complex to somehow track and trace these pieces of leaked memory over time so that we can clean them up. Our next classic garbage collection algorithm is mark and sweep. It uses a free list allocator, just like reference counting does. The difference is that it's a tracing collector. That is, we're going to find live objects not by keeping a counter in each of their headers, but instead by chasing the objects from the roots of a program at a particular program point. We're not going to reclaim objects immediately as they become garbage. We're going to wait until some other point later in the program, maybe when we run out of memory, to chase and find live objects so that we can clean up the dead ones. So this means that objects are not reclaimed immediately. They remain unreachable, and that is, they leak until the storage is exhausted or until we decide to perform garbage collection. Once we actually do perform garbage collection, we're going to pause the program. This is a stop the world collection in its most simple form, and we're going to sweep through the entire heap space and find any of the non-reachable objects and put them back on the free list. So the garbage collector, is going to perform a global traversal of the live objects and then an entire scan of the heap space that has been allocated by the garbage collector to find the dead objects and return them to the free list. So like reference counting, we have a set of algorithms that implement mark sweep. All of them are depicted here, and you should understand each one. Basically, what happens is we keep a single bit in the header of each object. Typically, we manage these bits because the architectures today don't handle bits well. They handle bytes or words and much more efficiently. So we'll typically have more than one bit but we'll only use one bit for the marking of our live objects. So in our abstraction, we're just going to use one bit. When we run out of memory, we go to do an allocation and we find that we can't allocate any more space because we don't have any that's contiguous and large enough to hold the object we're about to execute. Where we then start at our roots and we chase all of our roots to form a live graph. As we discover objects that are reachable from our roots, we mark the marked bit in the header of that object. We then start from the beginning of the heap and we scan the entire heap, and any objects that we find that aren't on the free list and that don't have their marked bit marked are garbage, and we put those back on the free list. And then we return control back to the program to continue executing after we allocated the object that triggered the garbage collection. we, again, just to reflect back on the free list system that we talked about in the beginning, this free list would contain all of those new objects. If those new objects that we freed up have contiguous addresses next to those objects in the free list, we'll conjoin them and make them into bigger contiguous blocks for use for larger objects. The strengths of Mark's sweep algorithm are that cycles are handled normally. Any tracing collector can handle cycles easily. The big one, though, is over reference counting, is that there's no overhead placed on individual pointer manipulations. Therefore, it's overall better than reference counting. Now, one thing I want to point out here is that reference counting may have smaller interruptions if we're considering a stop the world collection. But overall, because of all the overhead, the tiny little small overheads that are attached to each pointer manipulation, the end-to-end time of a reference counted program is likely to be longer than that of a Mark sweep algorithm. The weaknesses of Mark sweep are that it is a stop the world collector in its most basic form. That is, computation is halted, and so you may have these large interruptions in your program as garbage collection is being performed. The other downside of Mark sweep garbage collection is that the asymptotic complexity of the algorithm is proportional to the size of the heap, not just the live objects. This is because the Mark algorithm is asymptotic, has asymptotic complexity proportional to live objects because we're just tracing the live objects. However, the sweep has to walk the entire heap area that has been allocated, and so the cost of your garbage collection is going to depend on where your program is and how much space it's allocated. The largest downside of Mark sweep is that it fragments memory. As we clean up dead objects, we leave big holes and break up the contiguous nature of the heap, and it makes allocation slow and complicated. And because we have to find the cells that have the right size, or we have to, join the cells. There's a solution that we'll talk about in the next slide to getting around fragmentation, but without that solution, we can actually hurt performance pretty badly by moving through all of memory and cache and upsetting the caching and paging of the program itself. The last one, downside of Mark sweep, is residency. As heap occupancy increases, the need for garbage collection increases, so it becomes more and more frequent. This takes processing cycles away from the application, and so performance degrades as residency decreases over time. The most typical extension of Mark sweep is Mark compact. This is an algorithm that adds one more phase to this garbage collector. That is the compaction phase. Every so often, not on every garbage collection, but every so often, a third phase will be added after the sweep phase to compact the entire heap or some large sections of the heap so that we can get rid of fragmentation. This is really nice because fragmentation impacts our allocation speed, so our allocation speed becomes faster. It improves locality of reference for a period of time when when fragmentation is low. But the disadvantage is that we require additional paths, and copying objects is expensive. If you have a lot of objects to copy, the pauses can be very, very long. And with that, I'll stop and we'll continue on with copy collection next time.